Hi everyone, my name is Nat Sommer and I'm a PhD student here at Mount Stromlo. It is a part of the Research School of Astronomy and Astrophysics at the Australian National University. I'm a PhD student, which means that that's essentially the highest level of student you can be before they start employing you. But on the other hand, I'm also kind of employed. So it's a very awkward phase in which I'm never certain whether to tell people that I'm actually studying or working. But the most important thing is that by doing a PhD, I am able to learn a lot about the things that I find really important. And I'm here today to talk to you about some of those things. So I want to talk to you about black holes. But before we get started on that, I want to talk to you a little bit about gravity. Now, gravity is a thing that, when you jump up, you keep falling down. And if you've done any physics in school, you'll probably have to draw these diagrams where you have your just ground, and then you have a box on the ground, and you always have to draw these arrows and say that, oh, this is gravity, and then that means that we have an opposite force here that counteracts that gravity. But gravity is really important when you start doing space, because that's really the most important force when you have that really big stuff that you have in space orbiting each other. So this diagram that I just drew, that's really based on the more old-fashioned Newtonian gravity, which is actually quite good, and it works when you're doing things that are on Earth and are slow and nothing really. But when you start getting out in space and you start going at really high speeds, you need something slightly better. You need Einstein's general relativity. And you may have heard about space-time. Maybe you've heard it from Star Wars, maybe from Star Trek, maybe you've actually learnt about it in school. I'm not sure what the curriculum is in Australia at the moment, to be honest. But space-time is completely real. And what I really want to do was to take the scarf and sort of just create space-time fabric for you. But I don't really have anyone to help me right here, so we're just going to have to deal with this board. So let's now draw this scarf in just like one dimension. So this scarf would be like this if I held it on this side and on this side. And if I hold it straight out, it's just going to be straight and it's all good. But what would happen if I tried to put something on the scarf? If I took a little ball and I placed it here and I pushed it, this ball would just go over to this side. But as it would do that, it would also create a tiny dent. So let's now take this ball and put it in the middle here. That ball, because it has mass and it's heavy, it's actually influencing this thing, this scarf, or this space-time fabric. Space-time. So if you have your ball here, space-time is actually going to curve ever so slightly around it because it has mass, and that's just how it works. And so what happens then is, if we put a very big thing here, space-time is going to have to curve a lot. And if you put a tiny ball here and try to push it, this ball is going to get here and then it's going to want to fall down here. And if we have this in 3D and try to, for instance, push this ball not from there but from further out here, it's actually going to start moving slightly start rotating around this thing before it starts falling down. But it only falls down if it moves slow. If it goes very fast, it can still just go past it, or it can just keep orbiting it. The reason that it would fall down sooner or later if you use a ball and just an actual fabric is because you have friction between the ball and the fabric. But in space, you have very little friction. And so if you have two balls like the sun and the earth that start bending space-time fabric and start orbiting each other, those things may actually continue orbiting each other as long as they want to. So this is what space-time works like. And the question then becomes, how would a black hole look in this? Now, usually I would actually ask you to answer me before I moved on. I'm not going to do that, but I have put down my information here if you want to, or you can use the chat that is on YouTube and try to send me a few messages if you want to ask any questions, either now or later on. So you're going to find me as NATALIAEIRE on pretty much all social media. So get in touch with me later if you're not following. So the bigger the thing we put up here, the more the space-time fabric is going to curve. And essentially what a black hole is when you have something which is very, very tiny, but it's curving this thing a lot. And our space-time fabric just goes way down to infinity. So black holes just do something very strange with space-time, and space-time is what we live in, and so that's why black holes are so very strange. They sort of don't make sense because they just ruin essentially the universe. But that being said, when this happens, what's scary is really this point here. Over here, you're completely fine. You can just travel back and forth as you like there. You're not affected over here. Now, another important thing is something we call escape velocity. So let's have a ball over here again. And we have a curved space-time fabric over here. I'm sorry for that very non-straight line. But now let's have a tiny ball here. And in this case, let this be Earth and let this be an astronomer. It's a very exciting astronomer with a hat. Now this astronomer wants to leave Earth on a rocket. Well, as you know, if I just jump up, I keep falling down again. But as you also know, we have had astronauts in space, so that means that we must have been able to escape Earth somehow. And that brings us to escape velocity. So escape velocity is just how fast do you have to travel in order to escape something. Now for Earth, I believe that is 11.2 kilometers per second, which is pretty fast. That's why you're actually in a rocket and you can't even use an airplane. But as this thing in the middle here grows bigger and more massive, you have to travel faster and faster and faster. And when you get to the point where you have a black hole, this velocity here is actually equal to or greater than c, the speed of light. And as you may know, nothing in the entire universe travels faster than the speed of light. And that obviously causes a problem because that means that if you fall down here, there is absolutely no way in the universe that you can get out. And that's also why we call them black holes, because as you may know, when there is no light present, you have the absence of light, which is darkness, or blackness if you wish. Thus, black hole. Alright. So, how would we go about making a black hole? Well, the way that usually happens in space is that you have a very big star. And there are several ways this can do it. I'm going to explain to you one of them. You have a very big star, and that star becomes so big that gravity is sort of not quite dealing well with holding on to all parts of it. And it starts doing this sort of vibration thing, and it's sort of like gravity is trying to pull it together, but then you have an electromagnetic force, a radiative force that's trying to push it out, and sort of doing this thing up and in and out until it sheds out the outermost layers, and what's left inside is sort of just collapsing on itself, because in that part you no longer have the same type of electromagnetic force to push it out. As you do that and it collapses in on itself, you get what we call a neutron star. Neutron stars in itself are very, very strange because they are particles, they are stars which are made out of just neutrons. So where you usually had atoms with protons and electrons as well, the electrons have essentially been pushed into protons to create neutrons. And so you just have this big nucleus really, which is really, really dense. Even there you do have electromagnetic forces. They are the electromagnetic forces between neutrons. And they are also very important, and they do help keeping the star in the round shape. But sometimes gravity can overcome even that. Now, as I told you, you have already had electrons being pushed into the protons. At that stage, it's really difficult to, start pressing things into each other even more to get even more compact. And so when this thing collapses in on itself, there's really nothing more sensible it can collapse into. And it collapses into a black hole that no one can ever escape again. So that is one of the methods that a black hole can be created. But there are other ways that could happen, and there are other things that could turn into a black hole. So as it turns out, anything could actually become a black hole. You could become a black hole, and I could become a black hole. So the only thing that you need to create a black hole is just a really, really strong compression. So you need something becoming very dense. And as you may know, if you have graphite, the stuff that you write with in your pencil, if you compress that hard enough, you end up with diamonds. These pretty things. And essentially, you have the same thing times, millions and billions that happen into a black hole. So if you want, you can take me and turn me into a black hole. You just need to apply enough pressure that take all of me, tens of kilos, I'm not going to tell you how many, and compress that into something which is less than an atom big. That way I could become a black hole too. The only issue with that is that those really tiny black holes, they're not very stable. They're going to evaporate very quickly. Whereas those that I told you about, that are made out of stars, are large enough that they don't just evaporate. The stellar black holes are still big-ish. So if you took the sun and compressed that into a black hole, I believe you would have a ball that's about the diameter of 10-30 kilometers, or that may be the radius. Anyway, size of a city, pretty much. But you do have black holes which are even bigger, and those are the black holes that I am most interested in. They're called supermassive black holes. Now these things are so large, they would take up the space of about our entire solar system, and the masses of those are about like 1 billion times the mass of the sun. So these are really big things, and I'm very interested in them. But first I figured I would tell you how you should behave around a black hole. So black holes, they're kind of known for being sort of vacuum cleaners that, wherever you are, if there's a black hole, they just suck everything up. I've gotten questions from people about if there are black holes, why haven't we sucked up in one yet? That's because black holes aren't really that scary, because they work just like anything else. If you took the sun and compressed it into a black hole, created the same thing using the same kind of mass, only use pressure to make it smaller, we on Earth would be perfectly fine. There would be nothing wrong with us, because it's just the mass that we're orbiting around. The mass is the same. I mean, obviously, if the sun was a black hole, it wouldn't be as bright here and we would freeze to death. But that's a whole other thing. We would definitely not be sucked into it. So if you're around a black hole and you're far away, you're completely safe. No worries. The thing about a black hole is that if you do approach it, you're in trouble. But I mean, think about it. If you approach the sun and came really close to the sun, you would get sucked into the sun, right? It's not like you would be able to just stand above the sun and like, haha, I can jump up and down and I'm completely fine. No. Just like we are stuck on Earth, you would be stuck in the sun, and that's the same way you would be stuck in a black hole. The only difference about a black hole is that once you get there, there is no going back. That being said, falling towards a black hole is not really a pretty sight. So let's imagine that I now am falling towards a black hole, and I'm falling feet first. So the black hole is beneath me and I'm falling down. What is going to happen, and what's actually happening right now even on Earth, is that the part of me that's closest to the center of, a lot of mass, so the Earth or the black hole I'm potentially falling into, that part is actually experiencing a higher amount of gravitational force than the top. That's because just of how the gravitational force works. So you have that this is proportional to your mass and the mass of big thing divided by r squared. And that just means that the bigger something is, the stronger the gravitational force is, and the closer you are, the stronger it is. Now on Earth, I can't really tell the difference between the gravity on my feet and on my hand. But as I start approaching a black hole, you are going to tell the difference. And remember how we had this thing here, where we are completely fine here and we sort of have a black hole here? As you start approaching this thing here, you're actually starting to fall faster with your legs than with your head. And that sounds kind of weird. And it does sound like maybe you should be worried, and you should. Because what happens if your feet are falling fast on your head is that you're being stretched. And I mean, at first it can be kind of nice, like I like to stretch in the morning, but very fast it's going to be, go from, oh, it's a nice, crackle in my knuckles to, oh my gosh, I should not be this long. And this is a process we call spaghettification, because you're being drawn out onto a point where you look like a piece of spaghetti until, your body snaps in half and there is essentially blood and guts everywhere. So my personal opinion would be try to stay away from black holes. But then again, that would be fairly easy because most black holes are rather far away from Earth, so you're safe here, definitely. But let's talk a bit more about supermassive black holes, those things that I'm so interested in. The reason I'm very interested in them is, well, partially just because they're crazy. They're so big, and as it turns out, they are pretty much the most violent places in the universe. And I also think they're very interesting because, in a way, we can't explain them. There are some black holes out there that are so massive that it sort of doesn't add up. When we do the maths, it looks like there is no way for them to have grown to be that big since the beginning of the universe. And some of my research is going to go into trying to figure out how have these things evolved. How can they be this big? Now, another thing that we can use it for is to try to probe something called dark energy. And I'm trying to tell you a bit about how that works. So right over here, I'm going to draw you a black hole. In my case, it's pink. That's just because I don't have a black marker. But this is my black hole. And I'm just going to say BH for that. Now, black holes have usually a kind of disk around them. It's called an accretion disk. Accretion disk. And what this is when you have a lot of things that fall onto a black hole, those things can't fall into it simultaneously. So think about it. Imagine that you had a really big pool, or just a bathtub at home, and you filled it with water. Now, if you wanted to empty that bathtub, you wouldn't be able to do it very quickly. You would pull out the plug in one end, and it would take a lot of time for the water to actually go down the drain. This is essentially what happens around a black hole as well. You may have a lot of things that want to fall onto it, but because the black hole is so small, it takes some time. And so while the things try to fall into the black hole, they start orbiting it. And they create this disk around it. They try to fall down, but then they just start going in this ring over and over again until they can finally drop in. Now, think about this. Over here, we have a lot of things that are moving together. When you have that, there is chaos. There is craziness around. And what happens is that all of these things, they start smashing into each other. Now, think about this. Don't do this, but think about it. If you went ahead and just slapped someone really hard across the face, or someone did that to you, what would you feel, both in your hand and on your face? Like, yeah, it would hurt, but it would burn. You had a burning feeling. It's because it's warm. So this is friction. Things that crash into each other get very, very warm. And as things get very warm, they heat up. And as things heat up, they actually start glowing. Like, that's how a light bulb works, right? And so actually here, even though we have a black hole, and that's like the blackest thing in the universe, you have so many things trying to fall onto this black hole that thing actually starts burning really, really bright. And it turns out these things, this accretion disk around a black hole, that is the brightest thing we know of in the entire universe. And that's pretty cool because if they are that bright, we can see them very far distances. And that's something I'm very interested in. So what we like to do with things that we see very far away is try to turn them into something we call a standard candle. So I hope that you guys have heard about flux and luminosity. So luminosity is sort of an absolute brightness. It's how bright something is. If I have, a light bulb that is, 50 watts, that's going to be 50 watts wherever. But if I take that 50 watt light bulb and place it just in front of my eye, it's going to seem extremely, extremely bright. Whereas if I put it across the room, that light bulb is going to seem just fine. And that's because flux goes down as a function of distance. And so what we as astronomers like to do is to find things that we can figure out how luminous are. We can figure out the intrinsic brightness, figure out how many watts our light bulb is, so that when we compare it to our flux, we can figure out how far away it is. So if we know that something is, say, 50 watts, but it looks like it's just, 40 watts, we can draw this line here and find that, this thing is at, a 1 kilometer distance. And this is what I would like to do with these things, with black holes. People have been trying to do that for a long time, but it has been very difficult. The way that I do it is I'm actually using a kind of echo. So I'm over here watching this, and I see light coming towards me from this accretion disk. But a bit outside from the accretion disk, I have various clouds. We call them the broadline region, but it's not that important. What you really need to know is that these clouds essentially work as a mirror. And that way, this light from the accretion disk can go to these effective mirrors and then be reflected over so that I can see them from there. What happens is that I see this light coming to me twice, both from here and from here. Of course, this light takes a bit longer for me to reach me because light travels at constant speed, and this light had to go up here first before it can travel towards me. But if I'm able to figure out the delay between the first original light and the second light, I can translate that to a travel time, which means that I know the travel distance here. Now, this size here is actually dependent on how luminous this thing is. And so, if I can measure a time delay, I can actually translate that into how luminous my black hole is. But that means that I have a way to figure out how luminous something is without looking at the flux of something first. So I can find a luminosity and compare it to a flux and figure out just how far away these AGN are. And that's really exciting because that means that I can use them as standardizable candles, which means that I can learn about things far out in the universe. Because if I know the exact distance to them, I can figure out what's actually happening in the universe and how the universe works. And that way I can try to test cosmological models, figure out what is actually going on in the universe as a whole, figure out what the universe is made out of, what is dark energy, which is a thing that we find 70% of the universe is made up of. And we would really like to know what that all is. And this is what I hope to be able to do by me studying black holes. Now, I'm just about to run out of time, but I do see that I have gotten a couple of questions. So, the first question I got was, if you get a large enough blob of anything at a given density, will it become a black hole if you can collect enough of it together, whether it be iron or water or interstellar gas? And the question is yes. Anything, if you just press it hard enough together, the atoms will just go into a position that doesn't make sense to us. It will just all fuse into each other until there is nothing left, and it will become a black hole. The second is, does the density required to form a black hole decrease as you get more matter in the same spot? i.e., isn't a supermassive black hole less dense than a micro black hole? That is actually correct. So that's why I didn't tell you a number of how dense something must be to create a black hole, because it sort of depends on how big this thing is. I don't have time to go much further into that, but yes, good question and correct answer to your own question. The last question I've gotten here is, how do you search for black holes in space? That's actually really cool because black holes are black, and look into space, it all looks pretty black, so it's kind of difficult to find black on black. But we can look for bright things, and as you may know, if we can see something orbiting something else, we can figure out a lot about what's inside it. So if we have something here, we can't see that, but we see something traveling this orbit. And we know how big this orbit is, and we know the velocity here. We can figure out how massive this thing in the middle is. We can also figure out where this thing is. This is how we actually found the supermassive black hole at the heart of our own galaxy. So we saw some stars that were orbiting something, and at some point we realized that whatever they are orbiting must be, this radius is very, very, very small. But we also knew that that thing in there is really, really, really massive. And when you do the maths, you sort of just realize that if something that massive has to be that small, because whatever is orbiting it, the orbit obviously must be larger than the thing in the center. You realize that something so massive and so small can only be a black hole. That's my favorite way of finding supermassive black holes. And with that, I think I just have to give up because it looks time's up. Thank you all for coming in and having a chat with me. Look forward to seeing you again at some point in time.